Okay. Hi. Bonjour. Merci d'être venu. Thank you for coming for this sort of extra class. So I just wanted to show you some advanced results from many-body theory. So it's a little bit too much for the first time, but I think it's important to know they exist and know a few theorems and so on. So I will try to show you the Luttinger Ward functional and the Kadanoff Baym functional, and show you that they can be the basis for approximations that satisfy conservation laws and thermodynamic consistency. And in addition, there's a slight generalization of this that allows us to derive the dynamical mean field theory in a way that is very general and I find extremely interesting. Now, even this, I don't think I will have time to run through this, but I will try my best. And then there are things that I'm sure I will not have time to discuss. So Luttinger's theorem is in my notes, conserving approximations as well. Ward identities that are a consequence of conservation laws are in my notes. Migdal theorem is not in my note. And everything else is in my notes. So I will start with the Luttinger Ward functional. These two things are sort of mathematical niceties that allow you to prove things more rigorously. So I'll start by what's the most important result. So let us remind ourselves that we defined Z of some source field, Z of phi, as a trace of E to the minus beta k, where k is h minus mu(n), times the time-ordered product of the exponential of psi dagger 1 bar, phi 1 bar, 2 bar, psi 2 bar. And so you see that if I define the f of phi as minus t times the log of z of phi, when phi is equal to 0, I get the usual partition function, and I get this is the free energy. So at phi equals 0, this is the free energy. And as a functional of phi, I can derive, I can do the functional derivative of f of phi, and I put here 1 over the temperature. So delta phi, let's say 2, 1, is equal to G 1, 2. So these are all things that we have seen already. I just defined the free energy. So the free energy as a functional of phi is a generating function for the Green's function. And now well, okay, I will show you where these are come in, but let's go immediately to the Luttinger Ward functional. So you're used in thermodynamics to do Legendre transform. We go from the energy that's equal to TdS, dE is equal to TdS, and we go to F that's equal to E minus Ts, and dF is equal now to minus S dt. So using that T is dE ds, and this relation, we get this with S equals minus df dt. Okay, and that's called a Legendre transform. So here what we will do in this approach is to do the Legendre transform of this object. Why do we do this? We do this because we want to get a functional of the Green's function instead of a functional of phi. And it will give us an extremum principle also that is, well, similar to a sort of variational principle, but it's not really variational. It's just an extremum. So here to the Legendre transform then, okay, is based on this relation here, and on we defined omega of g as f of phi minus a trace of phi g. So now, in other words, we want to go from phi to g. And to eliminate phi, we use this relation. So we will have that delta omega delta g 2, 1 will be equal to minus phi 1, 2. Okay, it's similar to what I showed for the free energy. So to show this explicitly, we can show this explicitly. If I take the derivative here, functional derivative of f of phi with respect to g, well, I don't know how to do that. I have to do delta phi 1 bar 2 bar times delta phi, sorry, this doesn't look like a phi, delta phi 1 bar 2 bar times delta g 2 1. And now I have to define what I mean by this trace here. So the trace is defined by temperature times phi 1 bar 2 bar g of 2 bar 1 bar. You see, it's like matrix multiplication. Okay, so I sum over 2 and I sum over 1. And I have the temperature here just because the F have the temperature. So here I will, okay. So I need the 1 over T, no, okay, let me do it like this way. So that's the first piece. Then I have to functionally differentiate this, and there are two contributions. Okay, so I will do 1 over T here, and then 1 over T here. And then that will get rid of this T. And when I take the trace, I get minus. So I functionally differentiate this first. Delta phi 1 bar 2 bar times delta g 2 1 times g 2 bar 1 bar. And then the last term is obtained directly this way. So the t is disappeared, and I have the minus sign. The minus sign. So I have minus, and when I functionally differentiate this with respect to g21, I get phi 1 2. Okay. Now you see 1 over t times df delta f delta phi. I found this here. This is g 2 bar, 1 bar. Okay, so this is, if I look at this, this is G 2 bar, 1 bar. If you compare with this, you see that this disappears, right? Okay, so I'm left with this. So it's essentially the same proof as what you do in statistical mechanics. So this is it, yes. So we have to remember this. When you do a Legendre transform like this, then here you had the delta F, delta phi was G. So delta omega, delta G is minus phi, where these two are conjugate variables. Phi and G are conjugate variables. But I know what phi is equal to, right? If you remember from the, when we derived the equations of motion, when we derived the equations of motion, we found that G minus 1 was equal to G0 minus 1 minus phi minus sigma. So minus phi is equal to G12 to the minus 1 minus G0 minus 1, 1, 2, and then plus sigma 1, 2. Okay, so this, you see, I have an extremum principle now. This here, that is a functional of G, is equal to 0 at equilibrium. Okay, because at equilibrium, phi is equal to 0. So that's an extremum principle. And to find G, and that's why I would need these two things. But now I will proceed as if it had been proven. So here, this G minus 1, so I will write that omega as a functional of G is equal to the integral of this, right? So the integral of this is minus trace of the log of G minus 1. And that's the integral of this. And this is minus trace of G0 minus 1 minus G minus 1 times G. And here is plus phi of sigma. A phi of G. I'm sorry, that's a phi of G. But this phi of G is just such that, you see, if I functionally differentiate phi of G with respect to G 2, 1, it will give me sigma 1, 2. So to show that this functional exists, I need to show a curl property of sigma. I need to show that delta sigma delta G, well, yeah, I need to show that delta sigma 1, 2 delta G 3, 4 is equal to delta sigma 4, 3 delta G 2, 1. So that the in other words, if you take the functional derivative of this with respect to G on 2, it's equal to this. But now if you functionally differentiate again with respect to G 3E4, then you see you could have decided that this was the self-energy of 4, 3. Okay? And that would have functionally differentiated with respect to 2, 1. So this property has to be satisfied if this functional exists. And so if I have time, I will show you this proof. But basically, it is a consequence that this curl property exists for the for this functionality for f of phi. If I if I functionally differentiate this with respect to 2, 1, I get G1, 2. If I functionally differentiate once again, I get the functional derivative of G, and then I could have done it the other way. And because this property exists, this one exists as well. Okay, so for now, we will just assume that we have proven this property. And it means that this functional exists. So it's called the Luttinger Ward functional. And this one here is called the Baym-Kadanoff functional. Okay, now you see, let me talk a little bit about the other terms. If there are no interactions, there's no self-energy, and this phi is 0. So it means that when there's no interaction, we need to recover this omega of G is just the free energy of a non-interacting system. So if G is the non-interacting Green function, so this becomes a 0. So we have just this that is left. And it is indeed the free energy of a non-interacting system when expressed in terms of a Green function. So you see, we need to, if you functionally differentiate this with respect to G, you will get 1 over G minus 1, which is G. And yes. And then you look at the and then you differentiate with respect to G, and you get this G minus 1. So it looks as if just it was an ordinary integral, right? It's not obvious, but I will show it a little bit later if I have time. But just have to remember that it looks like an ordinary integral. Okay, so what is this? Well, let me find an expression for phi. Okay, so I've shown you the Luttinger Ward functional and the Baym-Kadanoff functional, and I can give you an explicit expression for this this phi. So the way it works is that the way it works is that I multiply the interaction term by lambda. Okay, we have done that already. And the real theory I want is for lambda equals 1, right? So it means that if I now differentiate an ordinary derivative of f of phi with this, I have a new, just a number here, a scalar. I differentiate with respect to lambda at fixed phi. What do I get? I get the expectation value of the potential energy. Okay. But the potential energy for a theory, so that is that has lambda in front of the interaction. Now, if I differentiate now omega, because what I want in the end is phi. If I differentiate this omega of g lambda with respect to lambda at constant g, I get the same thing. I get v of lambda. Lambda is here. Okay, so think of the thermodynamics again. If I have dE is equal to TdS minus PdV, I have dF is equal to minus S dt minus P dV. So it means that the pressure is equal to E minus dE dV at constant entropy, but it's also equal to minus dF dV at constant temperature, right? So I have to, here it's S I have to keep constant because S is the variable. Here it's T that I have to keep constant. Here it's the same thing. I keep phi constant, and here I keep G constant, and I get the same thing. Okay? Okay, so given this property of Legendre transforms, then it means that I can write that omega of G, at lambda equals 1 minus omega of G at lambda equals 0 is equal to the integral from 0 to 1 d lambda of 1 over lambda of lambda v evaluated at the theory where the interaction is, for the theory in which the interaction is lambda v. Now, if I look at the theory for that as lambda equals 0, what is the value of this omega when lambda equals 0? Well, when lambda equals 0, there's no interaction, so this disappears. There's no self-energy, and I get this because remember the G now is fixed. It's not necessarily the non-interacting G. It's a G, but it's fixed. So it means that when I subtract lambda equals 1 from lambda equals 0 in the theory, I just get phi of G. So this is the functional of G. And you see that it is universal in the sense that if I have a different non-interacting part to the Green's function, as a functional of the G, whatever G is, it has the same structure. In other words, the functional derivative of this phi with respect to G is the self-energy. And we know the self-energy is one particle irreducible, and we express the theory in terms of skeleton diagram. So this one is just two particle irreducible. So for example, that would be one diagram that comes in the calculation of this energy here. And if I functionally differentiate this with respect to G, I get the Hartree term. And if I, for example, look now at this term, if I functionally differentiate with respect to G, I get the Fock term. Okay. And this is two particle irreducible in the sense that I need to cut two lines here to split the diagram in two. And if you go to higher order, it's the same. Okay, so forget about this irreducible stuff and so on. The point is that we have an explicit expression for that, and this is universal. So now let me move immediately to this self-energy functional that will allow me to derive dynamical mean field theory in another way. So we like Legendre transform. So this is a functional of G, this Baym-Kadanoff thing. So let me look now, let me define a functional of sigma of the self-energy. Okay. So you see that I can define now if I look at this, now if I look at omega as a functional of sigma instead of a functional of G, assuming I can do that, which is not as obvious as in statistical mechanics. So if you can do that, then this is equal to or minus a trace of the log of minus G0 minus 1 minus sigma. Okay, that's this term. And here I have minus trace of, if I look at this, G0 minus 1 minus G minus 1 is equal to sigma. So I have minus trace of sigma G, that's this term, and then I have plus plus phi of sigma. Okay, so what is this? This is the Legendre transform of that functional. Okay, if I take these two terms together, this is the Legendre transform of that functional.
So if I define this as a functional here, this was a functional of G. I'm sorry. This was a functional of G. And of G of sigma. But I prefer to write it this way because then it's clearer that if I look at, for example, P, if I define this as P of sigma, then the functional derivative of P of sigma with respect to sigma will be equal to sigma 2, 1 will be equal to minus G12, right? Why? Because I have that delta phi, the functional derivative of the Luttinger Ward functional was equal to sigma. So if I take its Legendre transform like this, then the functional derivative with respect to sigma is minus G. Just the same proof as before. Now, now what happens if I take the functional derivative of this omega with respect to sigma? Then I take the derivative of this. So this is equal to minus, well, the log does not matter really. The minus here, I mean, doesn't matter really. It just makes this a real number when you actually compute that. But when we differentiate, then it's not important. So when I differentiate here, I get this minus sign is in front. Then I get 1 over G0 minus 1 minus sigma. And then I take the functional derivative with respect to sigma, so that gets rid of that sign here. And this is so when I take functional derivative with sigma, this forces this. Here I should have functionally differentiated with respect to 2, 1. So this will be the 1, 2 element of the inverse of that matrix with a plus sign. But then when I functionally differentiate this, it's equal to minus G, right? 1, 2 again. So it means that this obeys an extremum principle with respect to sigma. So delta omega delta sigma is 0. In the same way that it was equal to 0 when I functionally differentiated with respect to G, it's equal to 0 when I functionally differentiate with respect to sigma. So it's 0 when it's 0 at equilibrium. Because it's only at equilibrium that G0 minus 1 minus sigma is equal to G. The way I have the Dyson equation here, it was equal, I forgot to point this out. When I functionally differentiate this with respect to G, I get Dyson's equation. And at equilibrium only. It's only at equilibrium that Dyson's equation is satisfied because it's equal to 0. So here in the same way, this is equal to G only at equilibrium because it's only at equilibrium that Dyson's equation is satisfied. Otherwise, it's a functional. You know, I just, if I write this as a function, a G function here that have anything to do with any theory, I mean, it's just a functional of G. I can replace this by any G, right? So here it's the same thing. It's a functional of sigma, and when I am at equilibrium, I replace this sigma by, it satisfies the Dyson equation, and then it's at equilibrium that it's equal to G. Okay. So how do I get the dynamical mean field theory now? Well, I argued that this functional of G, given an interaction, given the form of the interaction in the theory, this is a universal functional of G. In other words, whatever G you give me, I write these diagrams and I get some number, phi of it. So that's the definition of a functional. You give me some function, I put it in the machine and I get a number. So here it's a functional of G. And it's universal. Given the interaction, it has the same structure. Whatever the G you give me, I will put it there and it will work out. So it means that the sigma, the P of sigma, that is the Legendre transform of this, is also universal. Okay? So the P of sigma is universal. So when we did the LDA, local, when we did the local density approximation, or if you want density functional theory, when we did that, we had some universal functional and we tried to find some, we approximated it as best as we can. Here, what we are going to do is to find the exact functional. This will be the exact functional, but not for the most general sigma. In other words, we are going to give ourselves some variational parameters. And for these parameters, the sigma will be the solution, the real solution of a theory. So it will be a real functional. So the trick to do that, so let me replace this by plus P of sigma, or yes. The only place that the non-interacting part of the theory comes in is in this G0. Okay. So if I change the one-body part of the interaction, let's say I have the infinite lattice, and with some U or whatnot on this, and all of this was connected. I'm going to change the one-body part of the interaction. In other words, I'm going to remove, for example, these links. And replace them by an infinite bat of non-interacting electrons. Okay. So these now are non-interacting electrons. I can, I have an infinite bat, and they can connect in all sorts of ways. So this is, if you want, I have variational parameters here that are related to how these things are connected. If I have an Anderson impurity problem, if I'm doing quantum Monte Carlo, then I have some hybridization function I can vary. So in other words, I'm going to look at sigma prime, and I have a G0 minus 1 of T prime, and this is sigma prime. Okay. So this is the exact functional for the solution to this problem. This problem I can solve exactly. Okay, I have this cluster and I have the bath of non-interacting electrons. And I know how to solve this exactly. So I know how to find this. So if I know how to find this, and I know how to find this because I can compute the self-energy and I can compute G0 minus 1 of T prime. So I can extract this. This will just be the difference between these two quantities. So now let's go to the real problem. The real problem is omega, and then I will use this sigma prime that has a limited set of variational parameters. And these are the variational parameters. I cannot vary sigma prime as much as I would like to. So it has a P of sigma prime. And it has minus trace log of minus G0 minus 1 of T minus sigma prime. Okay, now this is the real problem. I mean, I have an infinite lattice. Okay, here I don't, but here I have an infinite lattice, and the sigma prime now is the sigma prime for that problem. Okay, so I'm going to replace P of sigma prime by the difference between these. I mean, I put this on the left. Okay, so P of sigma prime will be equal to, let me do a little bit of artistic, take a little bit of artistic liberty. So this P, I get plus omega sigma prime plus this, okay? So this is an unusual way of writing an equation. So this is the right-hand side of this equation, okay? Okay, now the rule is that I need to minimize this. Well, no, extremize, I'm sorry. There's no proof that it's a minimum, but it's an extremum. So delta omega of sigma prime delta sigma prime 2, 1 delta sigma prime 2, 1 with respect to these variational parameters. So I can put 2 bar here. Now functionally differentiate this with respect to the parameters. It is equal to 0. That's now my new variational principle. I cannot variationally functionally differentiate with respect to all possible sigmas because I have a limited set of functional, excuse me, of variational parameters. But I can certainly do this. Okay, so if we functionally, this was an omega prime, I mean, this was a different theory. Now, if I functionally differentiate this with respect to sigma prime, what happens? This piece is 0, okay, because here I have solved the real problem, I have solved exactly a problem that has some G0 of T prime. So I have used an exact method. So if I take the functional derivative with respect to sigma prime of this, it's equal to 0. So, oh my God. Okay. I will have to erase this, unfortunately. So if I functionally differentiate this with respect to the t prime, you see that what I would get here is I would get the trace, and then I will get the 1 over G0 minus 1 of t prime minus sigma prime. And then I'm functionally differentiated with respect to sigma prime, so that the trace, in fact, disappears, except for the fact that I have n times over the size of the cluster. This term will come in a number of times, because what I've done is, I've replaced the full lattice by a set of disconnected cluster or disconnected sites. So I get this. Sorry. Let me put discrete indices or mu nu just for, and then I get minus sum over k tilde that came from the trace of 1 over G0 minus 1 of t of k tilde, that's for the full lattice, minus sigma prime. And I have again the same mu nu indices. And now I have the derivative of sigma prime mu nu with respect to these t prime variables. And that has to be 0 if I use this extremum principle. So if you think of these indices as a single index, then this looks like a dot product, okay? So this could be one way to have this equal to 0 is to have this vector here. Okay, this this multiplies these two terms, multiply this. So you can have one way is to have the vector equal to 0, perpendicular to this. Another way, which is the way that we will use, is to have all the components of this equal to 0. So if you have a way to find the exact solution of this t prime problem, then you can put this nc over n here, and then this becomes an integral because the lattice is infinite, and c is the number of sites in the cluster. So this becomes an integral in whatever dimensions you are, okay? That's ddk over 2 pi d. And now all the components have to be equal to 0. Now instead, if you don't have all the liberty to put all the components equal to 0, if you do continuous time quantum Monte Carlo, because don't forget there's some Matsubara frequency here as well. If you do quantum time Monte Carlo, you can solve this equation exactly. I mean, using an iterative method. But if you if what you have is, if instead of having an infinite bath of electrons, you have a quantum impurity problem, you know, a Anderson impurity problem where you put a lot of sites here, and you do exact diagonalization, like in the group of David Sénéchal. What you do is you have all these variational parameters that are these hopping and the bad sites and so on. So what you do is that you, okay, there's a sum over Matsubara frequencies now, IKM. And you take all of this, and you take the modulus square. So let me write this as really as like a modulus square. So the and then you look for the minimum over all parameters of the bat of this square. Okay, that's the best you can do if you don't have the full liberty of doing everything. So in the case where there's a single site instead of a cluster, well, this you recover dynamical mean field theory. Okay, so that's a really cute way of finding this. Okay, so here, what I mean by thermodynamic consistency, and I will just now throw at you a bunch of results that are proven in the notes without any proof. I was planning to take 1 week to discuss all these points, but I took so much, I was so late that we just have today. That was supposed to be the 13th week to get to all these points. So what I mean by thermodynamic consistency is that we know that we can compute, for example, the density, the number of particles, I'm sorry, by doing trace of the Green's function with the e to the minus I kn 0 minus. And we know that we can compute n also from minus the derivative of f with respect to mu. Okay. Now, the interesting, I mean, in many-body theory, there are many exact relations you can find like this, and it's as soon as you make approximation, it's basically impossible to satisfy all of them. But the statement is that if we take a Luttinger Ward functional that is obtained this way, so you take the full dressed Green's function and you can compute some phi of g. For example, the approximation of phi of g in that case could be that you take into account only these two terms. Okay, that could be one way. So, but whatever you do, as long as the Luttinger Ward functional is computed with some diagram, it has some functional, you will find that these two are satisfied. Okay, that this n is equal to this n. Now another problem is conservation laws. You see, if you suppose that I have the density at 0.1, and now I have psi at 0.3 and a psi dagger at 0.4. Okay, so if 4 is equal to 3, that would be the density correlation function. Now, if I take so I have some time ordered product, and if I take the time derivative of this, I know that there is a conservation law. So I need that plus the divergence of J of the current operator times psi 3 psi dagger of 4 will be equal to 0 as long as the dB tau acts on this. But in fact, it acts not only on this, but it acts on the time-ordered product here. Okay? So because it acts on the time-ordered product here, when I will get the equal time commutators, and in the end, I get the difference of two Green's functions. I don't remember the arguments here, but I get the difference of two Green's functions. So these are called Ward identities that are a consequence of conservation law. So you see that when you compute two particle quantities, they have to be consistent with one particle quantities in that way. So if you take a Luttinger Ward functional like this to compute your self-energy, you're guaranteed that this will be satisfied. Now, I don't want you to believe that this is a panacea, because there's an infinite number of approximations you can do for this, right? Depending how many diagrams you keep. Now, there are other identities. We know that the trace of sigma g is equal to the expectation of the potential energy. So if you start to cut to do approximations for sigma by cutting this Luttinger Ward functional somewhere, you will see that this is not satisfied. So you get killed at some point anyway when you do approximation. So what is Luttinger's theorem? So Luttinger's theorem is just the statement that at zero temperature, the volume of the Fermi surface is preserved by interactions. So we saw that the n of k at zero temperature, the expectation of let's say C dagger k, Ck at zero temperature, at the jump, right, whose height in z if there are quasi-particles. So Luttinger's theorem is the statement that, okay, you can define a Fermi surface this way, and the volume of the Fermi surface is conserved by interactions. So interactions can change the shape of the Fermi surface, but they cannot change the volume. And it follows from the existence of this Luttinger Ward functional. In fact, Luttinger and Ward, I think, derived that functional to be able to prove that theorem. So it was a sort of intermediate step in their case. So I talked about this. Now, Migdal's theorem is not in my note, but it's important for the BCS theory. And the statement of Migdal's theorem is that if you have electron-phonon interactions, so there's a phonon and there's some interaction, then vertex correction, so you have the phonon here, so that's a vertex correction. This is down by a factor square root of the mass of the electron divided by the mass of the ion. So remember that this ratio is 1 over 2000. So this is a small expansion parameter. So you can neglect vertex correction. So that's why in the Eliashberg theory works so well. So you have a phonon here, and you have a Green's function that breaks the symmetry. And you remember that we just said that this minus the self-energy, the Green's function, the difference between the two Green's function, the one of the non-interacting and the one now that has that breaks the symmetry and that contains these delta that depend on frequency. You put this equal to 0, and you get the Eliashberg theory, and it works very well because you were able to neglect vertex corrections. If vertex corrections had been important, you would have had some problem. So that's important for the theory of superconductivity. If you look at TPSC, we don't assume a Migdal theorem, right? Because there's a U spin here. that's different from the value. And so, I mean, there's no small parameter that we can use for just the Hubbard model in the normal state. Okay, so these are basically the advanced topics I did not have time to discuss, but that's nice to know if you want. Okay. So do you have any questions? Okay, so thank you for coming, and it was fun to teach you, and we will. You had some very interesting questions that every time I teach, I learn something new. So I'm learning just as much as you do, and I will see you on Thursday morning at 9 to discuss the last exam I gave and answer any questions you may have. And then I will mail to you the final at 9 o'clock on Friday, a French and English version. I hope they are consistent. I will do my best. And well, if there are misprints in the equations, it will be the same in the French and English version. So I will be available all day to answer questions, and I will find out a way. And then when you're done, you do whatever you can. You scan if you can. You take pictures if you cannot, and you try as much as possible to make a single PDF if you can. If you cannot, doesn't matter. And you mail all of this to me, and I will make the correction. And it counts. The final counts for only 30% of the note, so there's no stress. And it will have the same structure as last time. In other words, there will be two problems that are a little bit long or longer, and the rest will be a bunch of questions that are more, if you want, conceptual questions or questions that take 2 lines to answer, 2 lines of calculation to answer, and are related to how much you understand all this. Okay? Okay. So see you Thursday then. Bye-bye.
Bonne journée.
Ouais.
Bonne journée.